Welcome to the Deep Dive. We're here to cut through the noise and get you informed on some of the universe's biggest puzzles.
And today, we're tackling a huge one.
Yeah, absolutely. It starts with a question that seems pretty simple on the surface. If gravity pulls everything together, shouldn't the universe's expansion be slowing down?
That was the standard thinking for decades.
Yeah.
Makes sense, right? Gravity's the dominant force on large scales.
But then came this discovery, really mind-bending stuff revealing it's actually speeding up.
Exactly. Speeding up. It's a profound challenge, throwing a wrench into our fundamental understanding of physics. This wasn't just unexpected, it completely overturned cosmological models.
Forced us to confront something new, something invisible.
Right. Which leads us to today's topic.
Today, we are taking a deep dive into dark energy. That's the name given to this mysterious force driving the cosmic acceleration. It's one of the most significant puzzles in science, frankly.
It reshapes how we think about, well, pretty much everything from the largest structures down to the ultimate fate of reality itself.
So we've gathered insights from research, key articles, the whole story behind this astonishing discovery. We'll look at the observations, the theories, the Nobel Prize-winning work.
And our mission here is to guide you through it all. We'll unpack how the discovery happened, what scientists think dark energy might be, the big problems with those theories.
And even what the future might hold for the universe based on this. Basically, your shortcut to getting up to speed on this incredible topic.
Let's dive in.
Okay, so before 1998, the picture was pretty clear, or so we thought. Universe expands from the Big Bang.
But gravity acts like a brake, a cosmic brake, slowing things down over time.
Right. Scientists weren't debating if it was slowing, but really how much it was slowing down. They were trying to measure that deceleration rate.
Precisely. And to do that, you need reliable measuring sticks, cosmic rulers that stretch across billions of light years.
Enter the supernovae.
Type Ia supernovae, specifically. These aren't just any exploding stars, they're a very particular kind. They happen when a white dwarf star in a binary system pulls too much matter from its companion and hits a critical mass limit.
The Chandrasekhar limit, right?
Exactly. And because they all explode at roughly the same mass, they reach a remarkably consistent peak brightness.
Like a standard light bulb, a standard candle, if you know how bright it should be intrinsically.
And you see how dim it appears from Earth, you can calculate its distance. It's a cornerstone of cosmic distance measurement.
And you combine that with redshift.
Yes. Redshift tells us how fast something is moving away from us. As the universe expands, light waves from distant objects get stretched.
Making them appear redder. More redshift means faster recession and generally further away, further back in time.
So by measuring the distance from brightness and the redshift speed and time of these type Ia supernovae,
You could map the expansion history of the universe, see if it was slowing down as expected.
and that's where the surprise came in, a big one.
Okay, set the scene. 1998, two independent teams.
Right. The Supernova Cosmology Project, led by Saul Perlmutter, and the HISE Supernova Search Team, with Brian Schmidt and Adam Rees, both meticulously measuring distant supernovae,
Looking for that slowdown?
fully expecting to find it, but the data, it just didn't fit.
What did it show instead?
The distant supernovae were dimmer than they should have been, even dimmer than expected for a universe that was just sort of coasting without any deceleration.
Dimmer means further away than predicted for a given redshift in a slowing universe.
Which implies that something pushed them further away than expected. The expansion hadn't been slowing down sometime in the past. It started accelerating.
Wow. That must have been a shock. I heard Adam Rees had this moment with his computer program.
Yeah, it's a great anecdote. He was trying to fit the data to a standard decelerating model. The program basically needed to calculate the mass density required for the observed slowdown.
Yeah.
It spat out a negative number for the mass.
Negative mass.
Yeah.
That's not possible.
Right. As Rees said, computers don't know physics. But he realized it wasn't really negative mass. It was effectively negative deceleration, meaning acceleration. The universe was speeding up.
That realization must have been incredible, completely changed the game.
Absolutely. It turned cosmology on its head and deservedly earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics.
Okay, so the universe is accelerating. The next question is obvious. What is causing it? Enter. Dark energy.
Dark energy is really just a placeholder name. It's the term we use for whatever mysterious thing is responsible for driving this acceleration, its actual nature. Still one of the biggest questions out there, maybe the biggest.
And it's not just some minor component, is it? It dominates.
Oh, it completely dominates. Based on precise measurements, like from the Planck satellite mapping the cosmic microwave background, dark energy makes up about 68% of the total energy mass density of the universe.
68%.
Yeah. Then you have dark matter, another invisible component, making up about 27%.
Which leaves?
Ordinary matter, everything we see, stars, galaxies, planets, us making up less than 5%.
Less than 5%. Think about that. Everything we directly interact with and observe is just a tiny fraction of what's actually out there.
It's incredibly humbling. And what little we think we know about dark energy is, well, it seems to be very smoothly distributed, very homogeneous.
Not clumpy like matter.
No, not at all. It seems to fill all of space, even supposedly empty space, quite uniformly. And it's incredibly diffuse, not dense. Something like 10 to the minus 27 kilograms per cubic meter.
Almost nothing, yet it dominates cosmically because there's just so much space.
Exactly. And it seems to interact primarily, maybe only, through gravity. Its effects are really only apparent on the largest cosmic scales, probably undetectable in a lab.
So what's the leading candidate for what it actually is?
The simplest explanation, and the one built into the standard model of cosmology, goes back to Einstein. It's the cosmological constant, represented by the Greek letter lambda.
Ah, the thing he added to make his equations predict a static universe.
That's the one. He put it in back in 1917 because general relativity naturally predicted a dynamic universe, expanding or contracting, which wasn't the prevailing view then.
And when Hubble found the universe was expanding,
Einstein supposedly called lambda his biggest blunder. He thought he'd missed the boat on predicting expansion.
but now it's back.
It's back, big time. A cosmological constant is now the simplest explanation for dark energy. It represents a constant energy density inherent to space itself.
An energy of the vacuum.
Sort of, yeah. And crucially, this constant energy density has a weird property in general relativity. It exerts negative pressure, like anti-gravity.
A repulsive force.
Yeah.
Pushing space apart.
Exactly. And that's the core of our standard model, the CDM model. Lambda for the cosmological constant, dark energy, and CDM for cold dark matter.
Okay, simple explanation. Problem solved.
If only. Here comes maybe the biggest disconnect in all of physics, the cosmological constant problem.
What's the problem?
When we try to calculate the energy density of the vacuum using our other best theory, quantum field theory, the number we get is monstrously larger than the tiny value observed for the cosmological constant.
How much larger?
About 120 orders of magnitude larger. That's a 1 followed by 120 zeros.
Wait, 120 zeros. That's insane.
It's been called the worst theoretical prediction in the history of physics. It tells us there's something profoundly wrong, or at least incomplete, in our understanding of how gravity and quantum mechanics fit together. The vacuum energy is key, but we're missing something huge.
Okay, so if the simplest explanation, lambda, has this massive problem, what are the alternatives?
Well, one popular idea is quintessence. This suggests dark energy isn't a constant, like lambda, but something dynamic.
Like a field that changes over time.
Exactly. A scalar field, similar to the Higgs field perhaps, whose energy density can vary in time and space. It wouldn't be constant vacuum energy.
And that could potentially solve some issues.
Maybe. Some quintessence models have what's called tracker behavior. The field's energy density kind of follows the density of the dominant component radiation early on, then matter before eventually taking over.
Why is that interesting?
It might help with the coincidence problem, which is, why did dark energy only start dominating relatively recently in cosmic history, around 5 billion years ago? Why not way earlier or way later? A tracker field could naturally lead to that timing.
Interesting. What other ideas are out there?
Another whole class of theories doesn't introduce a new energy, but suggests maybe we need to tweak gravity itself. Modified gravity.
Changing Einstein's general relativity? That seems bold.
It is, but maybe necessary. The idea is that on cosmological scales, gravity might just work differently than Einstein described. Perhaps what we call dark energy and dark matter are just manifestations of gravity behaving unexpectedly over vast distances.
Or maybe dark energy isn't entirely separate.
Right. Some theories explore interacting dark energy, where it might exchange energy with dark matter or maybe even with normal matter, though that's more constrained.
So, lots of theoretical possibilities. But is everyone convinced dark energy even exists in the first place? Any skepticism?
Oh, absolutely. There's always healthy skepticism. Some researchers explore inhomogeneous cosmology.
Meaning,
The idea is maybe we live in a particularly empty part of the universe, like a giant cosmic void. Looking out from such a void could potentially mimic the appearance of acceleration without needing any actual dark energy.
like a cosmic mirage?
Sort of. Or perhaps the statistical methods used with the original supernova data had subtle flaws. These alternatives are generally considered less likely now, given other confirming evidence, but they're still explored.
And this connects to the Hubble tension, right?
Yeah.
It seems like a very real observational puzzle.
It really is. The Hubble tension is a significant disagreement about how fast the universe is expanding right now, the Hubble constant.
How does the disagreement arise?
When we measure the expansion rate using early universe methods, like analyzing the cosmic microwave background radiation left over from the Big Bang,
We get one value, around 67 kilometers per second per megaparsec.
right. But when we use late universe methods, like observing supernovae and Cepheid variable stars in nearby galaxies,
We get a different value,
mhm,
closer to 73.
and the uncertainties on both measurements are small enough now that they just don't overlap. They are statistically inconsistent.
Like measuring the same room with two different rulers and getting consistently different answers.
Exactly. And nobody knows for sure why. It could point to errors in one or both types of measurement, or, more excitingly, it could be hinting at new physics. Maybe dark energy isn't constant. Maybe it changes over time in a way that affects these measurements differently. It's a major driver for current research.
Okay, before we go further, let's quickly clarify something crucial. We've mentioned dark energy and dark matter. They sound similar, both dark, but they're very different beasts, aren't they?
Absolutely vital distinction. Dark matter makes up about 27% of the universe. Its defining characteristic is that it exerts gravity like normal matter. It pulls things together.
It clumps up, forms halos around galaxies, helps hold them together.
Precisely. It interacts gravitationally, but it doesn't seem to interact with light, hence dark. We know it's there because we see its gravitational effects.
Like gravitational lensing.
Yes, where its mass bends light from background objects. Or the dynamics of galaxy clusters, like the famous bullet cluster, where colliding clusters show the dark matter passing right through while the normal gas interacts and slows down. Clear separation.
And candidates are things like WIMPs or axions.
WIMPs, weakly interacting massive particles, were a long-time favorite, though searches haven't found them yet. Axions are another possibility, very light particles. Even primordial black holes formed in the early universe are considered. We still don't know what it is.
So dark matter clumps and attracts. Dark energy.
Dark energy, making up 68%, does the opposite. It's smoothly distributed and exerts a repulsive force, driving the accelerated expansion. Totally different roles.
Got it. Attractive versus repulsive.
Yeah.
Both invisible, making up 95% of the universe together in the ECDM model.
That's the standard picture, yes. SDM. Lambda for dark energy, cold dark matter for the clumpy stuff. It fits observations remarkably well, despite the theoretical puzzles like the Cosmological Constant Problem and the observational Hubble tension.
So how do we move forward? How do we try to solve these mysteries?
With better observations. Several major missions are underway or launching soon, specifically designed to probe dark energy and dark matter.
Like the Nancy Grace Roman Space Telescope.
Yes, Roman, launching hopefully late 2026 or early 2027. It's going to be incredible. Its wide-field instrument will survey a huge area of the sky, much larger than Hubble's view.
What will it look for?
It will measure tens of thousands of Type Ia supernovae out to great distances with high precision, mapping the expansion history in detail. This will be critical for testing if dark energy's strength has changed over time, if it's weakening, for instance.
And it does more than just supernovae.
Oh, yeah. It will also use weak gravitational lensing over vast areas to map the distribution of dark matter and how it's evolved, which also constrains dark energy.
And Europe has a mission already flying, right? Euclid.
Correct. ESA's Euclid launched in 2023 and is currently mapping the geometry of the dark universe. It's looking at billions of galaxies, covering the period when dark energy really kicked in.
How does Euclid work?
It uses two main techniques. Weak gravitational lensing, like Roman, to map dark matter distribution and its effect on cosmic structure growth, and also baryon acoustic oscillations, BAO.
BAO. What's that?
Think of them as frozen sound waves from the very early universe, which left a characteristic pattern, like a standard ruler, in the distribution of galaxies. Measuring that pattern at different times tells us about the expansion history and dark energy. Euclid will measure the positions and redshifts of tens of millions of galaxies for this.
And there's recent news from a ground-based instrument, too, DESI.
Yes, the Dark Energy Spectroscopic Instrument, DNII, it's creating the largest 3D map of the universe ever. Recent analysis from DSI has produced some tantalizing hints.
Hints of what?
The data suggests, though it's still preliminary, that dark energy might not be constant. It might have peaked in strength when the universe was about 7 billion years old, roughly 70% of its current age, and could now be weakening.
Weakening. That would be huge.
It would potentially, as they say, really change our understanding of what dark energy actually is, moving away from a simple cosmological constant.
And that directly impacts the biggest question of all, the ultimate fate of the universe. If dark energy is constant, like lambda, what happens?
The standard CDM prediction is the big freeze, or heat death. The universe keeps expanding faster and faster. Galaxies eventually get pulled so far apart they cross a cosmological event horizon we can't see them anymore. Stars burn out, matter decays, everything cools down towards absolute zero. Cold, dark, empty end.
Sounds bleak. But what if dark energy isn't constant? What if it grows stronger?
That leads to a scenario called phantom dark energy and the big rip. If the repulsive force gets stronger over time, it could eventually overcome gravity holding galaxies and clusters together. Then it could overcome the electromagnetic forces holding atoms together, and even the nuclear forces holding nuclei together.
Tearing everything apart. Atoms themselves.
Potentially, yes. Ripping the very fabric of reality apart. A dramatic end.
But the DSI hints suggest the opposite. Weakening dark energy. What if it weakens enough, even becomes negative?
Right. If dark energy were to decline, maybe even become attractive like gravity, then the expansion could slow down, stop, and reverse.
Leading to a big crunch.
Exactly. The universe collapsing back in on itself, perhaps ending in a singularity similar to the Big Bang, maybe even bouncing into a new cycle. Some cosmologists find that idea more appealing than an infinite freeze.
And the DSI results, though tentative, reopen that possibility.
They certainly make it more plausible than it seemed just a few years ago. It also circles back to the coincidence problem, why now? If dark energy is dynamic, evolving, maybe its peak just happened, cosmically speaking. The exact nature and future of dark energy are still very much up for grabs.
What an incredible journey we've been on. From that simple question about expansion to the shock of acceleration, the deep mystery of dark energy and dark matter, the competing theories, the observational hunt.
It really highlights how much we don't know. That 95% of the universe is made of stuff we can't directly see and don't fully understand is, well, it's a profound thought.
It really is. It's humbling, but also incredibly exciting, isn't it? It frames our place in the cosmos in such a stark way.
Absolutely. And if this new data hinting at evolving dark energy holds up, it changes everything about the future. Freeze, rip, crunch, the fate of everything hinges on the true nature of this mysterious force.
Or maybe, as some theories suggest, it forces us to rewrite gravity itself. The implications are just staggering. Finding the answer won't just tell us about cosmology.
It could unlock a completely new understanding of fundamental physics, the very fabric of reality. What dark energy teaches us could reshape everything we thought we knew. The quest continues.